Okay, here we go. So, got a pretty big problem right off the bat, but it's really simple actually. Okay, my buddy and I are standing in an ice rink. Okay, this is all about the third law, and you're gonna see a lot about ice rinks and like, I don't know, like objects like launching off of each other in the third law, but this is just something that I wrote up. My buddy and I are standing in an ice rink. I am 60 kilograms and he is 70 kilograms. I push with 210 newtons force. What are both of our accelerations? Let's read the entire problem to see like how we're gonna step through this. Let's say that I wanted him to get to the edge of the ice rink in 10 seconds. He is 3 meters away. What force should I push him with? How far will I be when my friend reaches the edge? And given the force from the first part of this problem, what would happen if I were wearing boots with really good traction on the ice? So that implies that there's no slipping, so I wouldn't move at all. How long would it take for my friend to make it to the end of the ice rink? Okay, so let's start with the first condition, which is 210 newtons, right? So you got, let's see, let's get out my handy dandy brush. So you got two buddies, right? You guys gotta slide away from each other, right? Let's say this is me and I'm 60 kilograms, and this is the other person, 70 kilograms. So you guys know Newton's 3 laws, right? Objects that stay in motion, stay in motion, stay at rest. Is at rest will stay at rest is the first one. That was a really poor way of wording it. But the second one is just F equals ma. And the third one is every action has an equal and opposite reaction. So that is our current focus today. So I am applying, let's see what my thing is. So I'm applying a force of 210 newtons, right, onto my buddy over here. That will imply that an equal and opposite force of 210 newtons will go back against me. And that kind of makes a lot of intuitive sense, right? Like, if this law didn't exist, that means like if I did a very gentle push, there will be like nothing counteracting my force. So that means I can infinitely push anything at all with like any force, and it'll be it just implies that you don't need to counteract any form of force. And as you can tell, like that means I can't stand on things because there's no normal force counteracting it. If I push on a wall, the wall will like fly off into eternity because there's no other force counteracting it. And like a lot of weird things don't happen without the third law. So we consider it to be quite important. But in this situation, you have the force of 210 newtons, and one is pushing my friend this way, which is the force that I exerted on him, and we have the opposite force going back, which is the action-reaction pair from me forcing him. So let's find out our accelerations, right? So I don't know how to say your name, Chinyer. Sorry about that, but this is like just really quick forces for your midterm test. Yes. So force is equal to mass times acceleration. So solve for me. Force 210 newtons is equal to mass 60 kilograms times acceleration. And that, I believe, let me just do some quick maths. Acceleration is equal to 3.5 meters per second squared, I believe. 180 to 10, yeah. And then my buddy, right? So 210, exact same force, no, is equal to 70 kilograms. So he weighs a little bit more than I do. And that's going to imply that the acceleration is going to be a little bit less than me, right? Like if you can imagine this intuitively, right? Let's say you have like a really big boulder, right, on the ice, and you flick a pebble at it. Then the you can imagine like the pebble's gonna like ricochet really far off, and you're gonna barely move the boulder. If it has more mass, it takes a lot more force to accelerate it. All right, and this is the exact same situation. So let's see, if I'm right, 210 divided by 70, acceleration is equal to 3 meters per second squared. Okay, sounds pretty simple, right? So those are our accelerations. Let me move this to, let me better adjust this. Ooh, I don't know where to put it. Let's just make it smaller. Put it to the side. Leave it there for now. Okay. Let's go to the second part. Let's say that I wanted him to get to the edge of the ice rink in 10 seconds. He is 3 meters away. What force should I push him with? How far away will I be when my friend reaches the edge? Okay. So this is connecting a lot of ideas, right? So you have Newton's law, action-reaction pairs. You have F equals ma, the second law. And once again, we have kinematics. And this is a relatively simple kinematics problem, right? So for this part, I should probably label the parts. Let's say that this is part A, this is part B, this is part C. Part A, part B. So you know that equation, x final is equal to x initial plus v initial times time plus 1/2 at squared. We simplify that to delta x equals 1/2 at squared, because x final minus x initial is delta x and v initial is 0. So you just simplify the entire thing to equal 1/2 at squared. And honestly, like 1/2 at squared is going to solve most of your problems. And if anything, you just add velocity times time to it if there's an initial velocity. But typically in these types of problems, it doesn't get too complex in physics 1 at least. Let's say that I wanted to get him to the edge of the ice rink in 10 seconds. Okay, so t is equal to 10 seconds. And delta x is 3 meters. Delta x is equal to 3 meters. Okay, so you have an equation with one unknown, which is pretty simple. You just plug and chug. And have a t squared is 100 seconds squared, right? And that's going to be, let's go. Hold on. What did I get? 10 seconds. Okay. 3 meters. 1/2 is 50, so 3/50 is equal to acceleration, right? I feel like that's a little bit small. Let me look through it again. Oh, so he's 3 meters away. That's 10 seconds is a lot of time. So I think that's like somewhat reasonable. So acceleration is about 0.06 meters per second squared, right? Okay. For some reason I'm skeptical of that number. I feel like that's really low, but oh yeah, 10 seconds for 3 meters. Yeah, that makes sense. That makes sense. Okay. So we have A is equal to 0.06, but that's of my buddy who is 70 kilograms, right? So force is equal to mass, 70 kilograms, times acceleration, 0.06. And that's going to be, oh, I don't like decimals, 4.2 newtons. Yeah, that's still very low. Let me check my acceleration calculation really quick to make sure everything is A-okay. 3 meters away. Okay, I think that does make sense. Okay, so it's just a really small force because it's such a small distance and you have 10 seconds to cover that distance. So that's quite a bit of time. So yeah, 4.2 newtons. So that means I'm also going the other way with 4.2 newtons. So me is 4.2 newtons equals mass times acceleration. So 4.2 over 60 is going to be acceleration. And I don't think you guys really care about the numbers, but I might as well just like plug it in. 0.07. So A is equal to 0.07 meters per second squared. And that's kind of suiting because once again, my acceleration is higher than my buddy's, which makes complete sense when considering that I weigh less than my friend. Okay. Are there any questions out there? Just making sure. I don't want to lose you guys too early. Let's see. Let's see if I can scale this. Oh, it's really simple. Ooh. I have no clue what happened there. But let's do this over again. Okay. Cut off a lot of it, but you know, you get the point. You get the point. Okay. Last part. Given the force. Oh, I'm supposed to find the distance. How far away will I be? I didn't answer the question completely. But it's just once again 1/2 AT squared, right? 1/2 times acceleration 0.07 times t squared is 100. 10 times 10 is 100 is equal to distance, and that's going to be 3.5. Distance is equal to 3.5 meters. And that's what part B. Okay, part C. Given the force from the first part of this problem, what would happen if I were wearing boots with really good traction? So there's no change in position for me. How long will it take for my friend to make it to the end of the ice rink? So what do you guys think? So first part, what was the first part of this problem? Okay. Oh, so first off, we need to solve for the acceleration, but okay, let's see. How long will it take for my friend? So how do you guys think? Which acceleration should we use? You guys have any opinion on this? You guys have any idea which acceleration to use? Like the only difference in the first situation and the second situation is that like rather than me moving the other way, I'm staying firmly in place, right? You guys have any opinions on this? It's pretty simple, but this is a little bit of a trick question as well. Just like a heads up. Anyone? Okay. I'm assume you guys all got it, but even if there is like whether or not the person exerting for, would you use it? Second situation? Oh no, I directly say the acceleration from the first part of the equation. So like the first part and the second part are like two different situations. I exert like completely different forces. So let's say that I exert so what I'm saying is that I exert a 210 Newton force on my friend, right? But I stay exactly in place, right? What do you think the acceleration is going to be for my friend? Like, do you think it would be the same? How do you think it would be different? And what other calculation do you think I would do in that sort of situation? Like whether or not I'm like standing in place or I'm moving. Either way, whether or not I'm standing in place or I'm pushing someone away, regardless, it's going to be 210 Newton force, right? So there is, like, even though I push against this person, and there's a 210 Newton force, ooh, my force diagram is kind of looking a little bit weird, but so we go back to this force diagram. This dude, well, this is me, is being pushed against 210 Newtons, right? But because there's frictional force, there is this 210 Newtons going the other way, right? But that doesn't matter when we consider this other person, right? It's this person still experienced 210 Newtons of force. right? The only reason why I stay in place is because there's another force being exerted on me that is completely situational to me, but not the other person, right? So whether or not I get pushed off and I'm flying off into the distance, or I'm staying right here, this guy's force and this guy's acceleration stays exactly the same. So for part C, I already calculated my buddy's acceleration, 3 meters per second. And once again, you can use your handy dandy 1/2 AT squared, 1/2 times, oh, this is second squared, 1/2 times 3 times t squared, where's the end of the ice rink? Equals 3, right? And then t is going to be square root of 2, right? Because if you just do algebra, it's pretty simple. You guys understand? Just check in. Okay, if you guys don't have any questions or anything, I'm gonna move on to the second part of the problem. Okay, so we have a really simple friction problem. Yeah, today I was told to do friction problems in Newton's third law, and sometimes I feel like the two are a little bit separate, so this might look a little bit different from the other questions that I have today. But this is an extremely simple friction problem, like the most fundamental level of friction problems. So we got a 20 kilogram block. Let's draw this 20 kilogram block because we love diagrams, right? The coefficient, we typically depict that with mu, right? Mu of static friction is equal to 0.2, and coefficient of kinetic friction, K, is equal to 0.1. And something I want to really point out right now is that the coefficient of kinetic friction is significantly lower than the coefficient of static friction. And that kind of intuitively makes sense, right? It should take more force to overcome, to get this block in motion than to keep it in motion, because if it were the other way around, that implies it's really easy to have it initially start moving, but really hard to keep it moving. Which kind of doesn't make any sense, because once it exits this regime of no velocity, it automatically enters the other regime. I think I'm not wording this correctly. I'm wording it in a really weird way. But you have to only it just takes more force over time. It can't take less force and then suddenly more force. Right? I'm just I don't know how to phrase this. But yeah, I think pretty much that's it. Okay, so I apply a 100 Newton force, right? Against this block. What is its acceleration? Okay, but let's draw our force diagram. We got normal force and force of gravity, mass times gravity. And we have friction force. So my question right now is, what direction is the friction force going to be? Is it going to be this way, or is it going to be this way? Also, a quick mention that I should say is that the friction force always opposes motion, right? So you might be saying, okay, so I'm not applying any force. Let's say that I completely neglect this 100 newtons right here, right? Let's kind of completely leave that out of the situation, right? Technically, there is still friction force. Okay, technically, there is still friction force between the block and the ground, right? It's just not active. So technically, it's zero force, but the magnitude of the friction force is very dependent on the magnitude of the force that's acting against. So yeah, so if it's below the force that it needs to overcome friction, then it's not going to move at all. But it's not going to be more than the force that is applied, because that implies that the friction is going to push it the other way. Okay, I think I'm really bad at wording things, so I'm just going to dive straight into this problem, right? And you'll see what I mean. Okay, so I got a 20 kilogram block, and the way you calculate force from friction is equal to the weight, which is like the force of a block's mass, times the coefficient, right? The thing is, we don't know whether or not it's going to move or not move, right? So let's first assume that it's not going to move at all, right? So let's see, coefficient of static friction. So we have 20 kg times gravity, 9.8 meters per second squared, as always, times mu, static friction, because we're going to assume that's not going to move at first. That's going to be, let's round this to 10, 10 to 40 newtons, right? So there is a 40 Newton force counteracting the motion this way, right? So it's overcome the coefficient of static friction because the applied force, 100 newtons, is far greater than the force counteracting it from friction, which is 40 newtons, right? So we know that it's going to move. Okay, so then that means it's going to be the coefficient of kinetic friction, which is going to be 0.1, and that's going to be, let's see, 0.1. I can't do math right now, but that's going to be 20 newtons. So there's 100 newtons pointing this way and 20 newtons pointing this way. That means if you subtract these two, because these forces counteract each other, so 100 newtons minus 20 newtons is equal to 80 newtons, right? What is its acceleration? And once again, we have 80 newtons is equal to mass, 20 kilograms, times acceleration, 4. Wait, I just solved it in my head, but that's acceleration, and when you solve it, acceleration is equal to 4 meters per second squared. Okay, I think that's pretty simple. Let me try to conjure up like a situation where I explain why it's impossible for static friction to be smaller than kinetic friction. Okay. Okay, so let's say that we switch these two, right? So let me make sure that you know that this is an impossible situation. Impossible, right? Static friction is equal to 0.1, and that's a really good thing. Kinetic friction is equal to 0.2, right? And then let's say, let me do some quick maths. I need to do some quick math to make sure that this does come out right. So let's say you apply a 40 Newton force instead of a 100 Newton force. Let's say you apply a 40 Newton force, right? Okay. So let's say it's 40 newtons, right? So we do the first thing, which is see whether or not it's staying in place. So mass times gravity, 20 kilograms times gravity, 10 meters per second squared, times coefficient of static friction, 0.1, is equal to 20, right? Yeah. So no, I was like making sure that my work is right, but this is just 20 newtons. And since we know that like the applied force is much higher than the coefficient, like the force of friction, we know that it's actually in motion, right? So when it's in motion, we can use the other force, 20 kilograms, times 10 meters per second squared for gravity, times 0.2, right? That's going to be equal to 40 newtons. So is this in motion or not in motion, right? So let's say that this is, okay, let's say we apply 35 newtons, right? It's overcomes static friction. So technically it should be in motion, but it's less than the coefficient of kinetic friction. So is it in motion or is it not in motion? It's physically impossible to have a situation like this, right? Because that implies that like once you overcome static friction, you can't even move. Then you're still static, right? So that's just kind of why it's physically impossible to have the coefficient of static friction to be less than the coefficient of kinetic friction. And that's just fun facts you now know about physics. Okay, I think that was pretty interesting, but let's go on to our third problem that I have prepared for today. I have a 50 kilogram block, a 30 kilogram block, and a 20 kilogram block sitting side to side in that order. Okay, let's show that. Okay, so the first block is pretty big, 50 kilograms. The next block is kind of a little bit smaller, 30 kilograms. Block after that is even smaller, 20 kilograms. Right, and they're all just chilling on like on the surface, right? And then I applied 200 Newton force to the right. Okay, so what are the forces between the blocks? So once you see forces, the thing you want to first do is force diagram, right? Okay, so you got this downward force, mass times gravity, and action and reaction pair, you have the normal force counteracting it, normal force, mass times gravity, mass times gravity. Let's just multiply out, and let's just approximate gravity to be about 10 meters per second squared. That's going to be 500 newtons, 300 newtons, and 200 newtons. Okay, you got normal force, which is in the equal and opposite direction, so this is 500, 300, and 200. And that's perfect because if it were different, that implies that it's in motion, right? And it's definitely not flying up into the air for some reason because we intuitively understand that's not happening. But we know that this block, if we think about how real world would work, if you push this block, all of these blocks will also move along with it, right? But then what's the force acting on this block? Well, it's going to be this force acting this way, right? But because there's an action and reaction pair, there's going to be another force counteracting it, going this way. And this is the exact same in this situation over here, right? There's a force going here to push this 20 kilogram block that way, but it's also pushing back against this 30 kilogram block this way. And that's called, once again, action and reaction pairs. And this happens in both horizontal and vertical motion. So that's why you still need to consider the force of this block counteracting it. Okay, so let's solve for the total amount of acceleration, right? So 200 newtons, right, is equal to mass. So we want to add all these masses together because this force is applied on this as like one body that we can imagine, right? So if this were like one solid object, let's imagine it that way. That'd be 50 plus 30 plus 20 is equal to 100 kilograms times acceleration, right? Acceleration is going to be 1 meter per second squared. And that's super convenient, right? So, okay. So we know that the force of this block, right? Because it's going at 1 meters per second squared, that this block is going to exert a force of force is equal to mass times acceleration, 50 newtons, right? Because on its own, if we completely neglect all the other parts, we know that this is going at 1 meter per second squared. So we know that this force out of here is going to be 50 newtons. However, that also implies that there is an equal and opposite force acting as 50 newtons this way, right? Okay, so that's the first block. So we know that these two forces, 50 newtons, 50 newtons. Okay, so how about this block, right? Smaller block. Ooh, my work is really messy. Let's move this here. Let's make this look somewhat presentable. Well, I'm definitely not helping this right now. Let's shrink this a little bit. I really enjoy MS Paint. I feel like it's the most powerful like picture editor out there. It's my favorite. Okay, so we have 50 newtons applied here, but we know that this is going to have 30 newtons because force is equal to mass times acceleration. It's accelerating at 1 meter per second squared, and if its mass is 30 kilograms, so the total force is going to be 30 newtons, right? And we know that there's 50 newtons acting this way. So 50 newtons, ooh, how does that do? 50 newtons plus let's call this force C. Force C is equal to 30, right? Because the addition of these two forces should balance out and equal the acceleration, right? So that force C is going to equal 20 newtons. And that perfectly fits because this is like 1 meter per second acting the opposite way. So that's pretty intuitive, right? Why that's 20 newtons. So let's just say there's an action-reaction pair. Oh, that's something from chemistry. I wrote a symbol from chemistry, but like you get what I mean. Don't use that on the physics test. But we have an action-reaction pair of 50 newtons here. And we have another action-reaction pair of 20 newtons here, right? And that makes sense because if you push this with 20 newtons, it's going to be 1 meter per second squared. Okay, so I think that was like mostly just like conceptual, making sure you understand how action and reaction pairs work, right? It's pretty simple, pretty intuitive. Okay, let's do another one. I'm floating in space with a zero velocity relative to my spaceship. Right, so I mean, like the Earth is spinning, so maybe relative to Australia, I'm going like super fast, but relative to my spaceship, I'm at zero velocity. And once you get deeper into physics, you'll understand why that's so important. I have to get back into my ship in 30 seconds, or else the ship will lock and return home without me. Once again, these physics problems are very absurd. I have a 20 kilogram boulder, and I am 100 kilograms, so once again matching with the absurdity of this question. The entrance to the shuttle is 4 meters away. What ends up being the acceleration of the boulder I throw? Okay. So first off, we need to find out how fast we need to accelerate back to our ship. So let's draw our ship, right? Do a cute little illustration because we feel special today. Okay, we got our little friend. He's in his spacesuit, and he's like kind of sad, and he has like this big old boulder that he's gonna throw this way to allow him to accelerate the other way. And yeah, that kind of makes sense because once again, like Newton's third law, action-reaction pair, if you apply a force this way, there's going to be an equal and opposite force being applied this way, and that force is going to accelerate you back into your spaceship, right? So if you're ever stuck in space, you know what to do. And this is actually a strategy that a lot of rockets utilize. If you think, just fun facts that I sometimes remember, right? So don't quote me on this. I went to NASA once. But you got like those very small like command whatever, and you have like these huge like fuel pods, right? And they detach the other way. So once all the fuel is burnt, it detaches the other way, and because of Newton's third law, it's gonna propel this entire thing farther forward, right? So we use force, release it, and because it's such a huge mass, there's gonna be a lot of force to it. That's going to allow you to propel your rocket forward, right? And once you're in space, because there's like nothing you can launch off of in space, there's no like large mass that you can propel off that would be substantial. You kind of need to like do it all on your own, right? There's no other force being exerted, so you gotta, and then eventually this huge thing comes off, and you further accelerate. And if you see the proportion of the mass, like this has a much larger mass. It's not even m, much larger mass than your command module. So quick facts about rocketry, right? Rocket science. I don't believe in rocket science because there's a difference in engineering and science. But fun facts about rocket ships. But once again, let's go back to our problem. I am floating in space with 0 velocity relative to my spaceship, so I'm stagnant. To get back to my ship in 30 seconds, so we have a t is equal to 30 seconds. Yeah. So first we need to solve for acceleration, right? Before we figure out the force. We need to figure out how fast we want to accelerate. We know that my mass is going to be 100 kilograms, but that's currently irrelevant. So we have delta x, well, delta x is equal to 4 meters. Once again, handy dandy 1/2 at squared. 4 meters is equal to 1/2 acceleration. Acceleration times time, 30 seconds squared. Then that's about 8/900, right? Let's get exactly, please. You know what? Let's round this to about 9-ish, 9/900, and it's about 0.01. Just because I want like nice even numbers to simplify things later on. So let's say our acceleration, you need to accelerate at 0.01 meters per second squared, right? Once again, I feel like this acceleration is really low, but I keep on neglecting that. I need to just travel 4 meters in 30 seconds. So, okay. Acceleration 0.01, right? And we need to figure out the force that I need to, like what force needs to act on me so I correctly get into the ship, right? So you're solving for force. We know that my mass is 100 kilograms. And we know that the acceleration is 0.01 meters per second squared, right? So force is just going to be 1 Newton. It's pretty good, right? But that brings up the question, how about my boulder, right? Well, the boulder needs to exert the exact same force, action-reaction pair. So 1 Newton is equal to mass 20 kilograms times acceleration is equal to 0.05 meters per second squared. All right, did I even do the math right? Yeah, that looks right. Is it right? Yeah, that's right. Okay, that's pretty much it. Any questions? Anyone ask anything? Okay. No one says anything. I'm gonna just keep on going. I am 100 kilograms. Okay. 100 kilograms. It's like a decent weight. It's like a standard adult, right? So 100 kilograms. I'm pulling a 60 kilogram crate. Okay, for the sake of simplicity, I didn't think about like angles or anything. Let's just assume that when I pull straight, 120 Newton force. But I'm only accelerating 0.2 meters per second squared. Right? What is the friction force acting on me? What is the friction force acting on the crate? Okay, so we want to find the total force, right? Let me try to find. So let me reread my question. So we have force is equal to mass, okay, 160 kilograms times acceleration to meters per second squared. Okay, so this entire thing is accelerating as like one system, right? So if I'm pulling it, that means I'm also moving this way. That's why we can use the force is equal to mass times acceleration. Is that it? Yeah, that's it. So the total force is going to be about 32 newtons, right? I didn't think hard about this question when I wrote it. Now I can see a couple faults with it. But I'm only accelerating at 0.2 meters per second. Oh, no, that makes sense. Okay. So there's a total of 32 newtons, right? So let's find the actual acceleration of this guy over here, right? So we have force is equal to mass 60 kilograms times acceleration, which is 0.2, right? So the actual force of what's happening is about 12 newtons, right? But why I'm applying 120 newtons and it pops out 12 newtons. That means there's something going on, and that's called the friction force that is opposing our motion. Well, I should probably put summation f x of the block b. Good notation is always good. Wait, no, that's just like that's the total force, which is equal to 120. So because it's going this way, we always want good notation, right? So the block is going to end up being moved this way. So I say this direction is a negative direction. Okay, as long as you keep your directions positive and negative, adding all your forces will be correct. You don't want to like mess up your signs. So negative 120 plus force of friction is equal to that, right? Is equal to 12. Wait a second. Oh yeah, negative 12. That's why. I was like, why am I getting positive where I shouldn't be? And force of friction is equal to 108 newtons, right? Okay. Let's see. I calculated the total force for no reason. Let's just delete that. Force of friction on the block. I can do the exact same thing for a dude, right? About 100 kilograms. Mass times acceleration. 0.2 meters per second squared is about 20 newtons. Yeah? So he's going this way at 20 newtons. But once again, I'm being pulled this way, 120 newtons. So where's the difference, right? So 120, because this is positive, this is going to the right, so it's positive, 120 newtons. Coefficient of friction is going to act the other way, right? Minus, what is it? Oh, coefficient of friction. Forgetting things. Is equal to negative 20, right? So force of friction would be about 100, right? And let's calculate for funsies, right? Let's calculate the coefficient of friction. Okay. So we know that the coefficient of friction is, the equation for friction is going to be mu naught, and because they're in motion, we know kinetic friction is times mass times gravity. And we know that this 100 newtons is equal to mu k times 1,000 newtons, right? Because 100 times 10 is 1,000, and this guy, 108 newtons is going to be mu times k, 600. Yes. You might notice something interesting, right? Mu k over here is going to be 0.1. Right? And mu k over here is going to be about, let's do 100. What's 1 over 6? 1/6? Yes. Wow, I actually did some math in my head. So mu k here is 0.1667, right? And you're like, but wait, why are these mu k's different, right? That's so weird. Okay, a couple of things. One, the first problem with this is that, like, the problem isn't like set up correctly, right? Like, this is a situation that probably wouldn't happen in real life because, like, for one, I'm probably wearing like really nice boots, right? So they probably have really good traction, and you don't know, maybe I put like some ice or like some like water here to decrease the friction, right? Also, another way to explain it is that you see when you pull something, right? Your feet are kind of like planted like this, right? And you're like pulling stuff, right? So the force here is at an angle, right? So the vertical force is ultimately, the normal force is ultimately going to be our frictional force, but there's a lot of extra force being applied that we don't consider. And we're doing an oversimplification of the system, right? We're just assuming that like the total frictional force is going to be completely, like all of our mass is completely vertical. Right? And that's kind of true, but like when we pull the thing, we go at an angle. So this isn't a completely realistic situation, but in physics, we can't have completely realistic situations because there's too many variables happening. And that's when you start using modeling and stuff, when you go deep into physics, right? Like when you go into, what is it? Like vibrations. This is just me going on like other cool physics stuff, right? Like you know how like in simple harmonic motion, like there's springs and stuff, and like they vibrate back and forth, right? Well, in reality, let me tell you, everything is made out of springs, right? And there, inside my body, there's millions, billions, and trillions of springs happening all at the same time. Like the systems are incredibly complex, right? But we can't do the math for all of them. So a fun fact about physics is that being a physicist isn't about like sitting down and doing these problems, right? You do need to understand it, but the systems that you deal with as a scientist is far more complex, and most of the calculations are done by computers. Fun facts. Okay, and like once you like have really complex systems, you can like calculate a lot of really cool things out there, right? For example, like resonance and stuff. But yeah, that's just like, it's just a really simplified form of a system. Okay, so we can do a fun question now if you guys don't have any questions from your like, homework or anything. But so everything is an action and reaction pair, right? So if I hit my table, right, maybe I'm applying like a 2 Newton force on the ground, right? But the ground is exerting a 2 Newton force back against me. But that implies that there is some sort of acceleration happening to the ground. So every time I pat the ground, technically the earth is moving a little bit, right? Like if you think about it intuitively, like our ice skater problem, right? I exert a force on my buddy and we both go off at the same force, right? Well, this isn't any different when you have a giant earth, right? And you're a little person over here, you exert a force, right? And if there's no gravitational force, which doesn't make much sense, if you even exert the tiniest force, you will move the earth a little bit. And you yourself will move a lot more because once again, your mass is a lot lower than the entire Earth's mass, right? But regardless, it does move a little bit. And the reason why we don't fly off is once again, gravitational force pulls us back in, right? So think about that. Like every time you like step on the earth or like jump on the earth, just like imagine the earth moving away from you just like a tiny bit, just like the smallest amount, right? But we can calculate that right now, right? Fun question, I am 100 kilograms and I jump with 2,000 newtons force. So that implies that let's assume that we jump completely vertically, right? So there's a force acting up on us, right? That's because that is in reaction to our force that we applied downwards, right? 2,000 newtons. 2,000 newtons, right? Okay, I'm 100 kilograms and jump with 2,000 newtons force. How far does the Earth travel before I land? Okay, so a couple of things. I'm 100 kilograms, jump with 2,000 newtons force. Okay, I actually didn't think about this hard enough, but let's see. I actually don't know how what's gonna happen when you jump with 2,000 newtons force, right? You know what? Let's just do an oversimplification of this problem, right? Because I don't want to like think about gravity and stuff. Like I didn't intend this problem to be like more complex than what it is. Let's say that I jump and I exert 2,000 newtons force. Oh, I see what I mean. Okay. So yeah, let's just do what I initially intended. If I jump with a 2,000 newton force, yeah, let's just go with the simplification. I feel like the other way is going to be like too complex. I don't want to like dive too deep into physics. Let's say I exert a 2,000 newton force once I jump, right? Because that's just like how it'd be like. And then I'm in the air for like 30 seconds, right? Oh, that's a really long time to be in the air for. Let's say 5 seconds. Okay, so let's see, 2,000 newton force. So once again, we can do F is equal to ma, right? You exert a force against the Earth, right? Which is 2,000 newtons. 2,000 newtons is equal to mass 5.972 times 10 to the 24th power. Force is equal to mass times acceleration, right? Okay, let's see. 2,000 divided by 5.972 divided by 10 to the 24th power, which is 3.34 e to the negative 22. Negative 22. Okay, so if you're in the air for 5 seconds, that is your acceleration, right? Let's do oversimplification of the problem once again, because that's like completely neglecting gravitational force and assuming that we neglect gravitational force, that this is acceleration. 1/2 at squared, right? Handy dandy 1/2 at squared. Always very useful. 16. And this will happen earlier. 1/2 at squared. So delta x is going to be equal to 1/2 times acceleration, 3.34 e to the negative 22 times, what is it, t squared, 25, equal to 12.5 times 3.34 e to the negative 22. That's really small. And that's exactly what you would expect, right? 41.75. Right, and let's do this in proper science. 4.175 e to negative 23rd. Oh, that's really small, right? That's like very, very, very small, like a tenth of like the size. What is the diameter of an electron? This is probably like around there. Diameter of an electron, let's see. 10 to the negative 18, right? And this change in distance is to the negative 23rd. So the change in like the distance of the Earth changes by like less than like the width of an electron, which is exactly what you would expect. It would be a little bit concerning if it were more than that, right? But the Earth does move. We can jump. Just a fun fact. Okay, let's see. Yeah, it looks like we have one question. Why isn't static friction subtracted from the force? Oh, sorry, I didn't like get to this question until like the very end. I usually ask questions at the very end, but it looks like they're gone. But I'm gonna ask at the very. I'm gonna still answer. I'm assuming that this is a second problem. Yeah. We only do that because we want to figure out whether or not it's static or kinetic friction. So we only get to choose that at the end. But yeah. Anyway, that's it for me this week. I think I talked about a lot of cool physics stuff, so I'm pretty satisfied. But yeah, thanks for coming in, guys. I like doing these physics problems. I like hanging out on Thursday nights, even though I do have a lot of other homework. But I'm very glad you guys came. Okay. Thank you. Bye.